So welcome everybody. My name is Gergő Turán, and I am a master's student at Eötvös Loránd University in Budapest, Hungary. And this talk will be about mechanised use of atomization in Erlang. And before I get too far into this, I want to say that these slides are very much so there is a lot of information here. So maybe it would be nice to only ask questions at the end of the slideshow. So before I get to the main part of this talk, I want to talk about formal semantics a bit, because I understand that this is mainly an Erlang-based audience, and some of you might not be that familiar with formal semantics. So formal semantics models the computational meaning of programs, and here is a situation that you might have run into during your work. Let's say you are given an expression in a programming language, and it could be in any programming language, not just Erlang, to evaluate. So you evaluate it and get back an answer. Then your colleague does the same thing, and they give a different answer. So what did you use to get these answers? Well, you both use your own favorite interpreters, compilers, or other tools that you might use. So logically, it would follow that one of your favorite tools didn't really follow the language specifications to the T. However, it turns out that both of your guys' interpreters or compilers claim to follow the language specifications. So what happened here? So basically, the problem here is the language specifications themselves, but they are usually given in natural languages, such as English. And the problem with natural languages is that they are complicated and ambiguous, and that is not surprising because people are also complicated, and sometimes they could be ambiguous. But fortunately for us, there is another way to give specifications to programming languages, and that involves a language that is unambiguous, that is mathematics. And formal semantics is all about defining the meaning of programming languages using mathematics. And there is also another catch here, which is that mathematics might be unambiguous. However, people still make mistakes in mathematics. So everything that you will see in this talk was also formalized in the ROC proof assistant. And if you don't know ROC, it was actually called COC for a very long time. And this is an interactive theorem prover based on constructive logic. And so if you implement your formalizations into ROC, then you can make sure that when you prove theorems, you don't miss anything during the proof of these theorems. And so once we have a mathematical way that we defined our programming languages, that is great for us because we can do a couple of things like proving properties of programs and also deriving formal tools based on this specification. So getting this a bit closer to home, at our university for the last 5 years, there has been a project going on called the High Assurance Refactoring Project, or HAR. And this is about proving refactoring is correct. And the main language in focus is Erlang because of its interesting concurrency model. And the main contributor to this project is Péter Bereczky, who made formal semantics for the Core Erlang language. And that was basically his PhD thesis. And so in this talk, you will get a bit of a taste of this Core Erlang semantics, and then I will be talking about formalizing atom exhaustion in the semantics, and then I will be talking about a calculus called Galois that was developed. So Péter's semantics actually formalizes Core Erlang instead of Erlang, and there are multiple reasons for that. So Core Erlang is further down the Erlang compilation pipeline than Erlang. So there are many features in Erlang that are just basically synthetic sugar, and during this compilation they get desugared. So there are fewer things in Core Erlang that need to be formalized. Another thing another reason to formalize Core Erlang is because it's also in the pipeline for other languages in the Bean family, such as Elixir. So this formalization of Core Erlang can also be used to reason about Elixir programs as well. And if you want to give formalization to Core Erlang, luckily for you, there is a specification available, and as you can see, it's really fresh and up to date. The last version of this file was made in 2004, so 21 years ago. So this file was used to formalize the language, and everywhere where it was not clear or it seemed out of date, the Erlang shell the Erlang shell basically decided what to do. So this is a short excerpt from the syntax of this semantics. So Core Erlang expressions can either be values or exceptions other than values. And values are things like integers, atoms, and lists. And non-values are things like function calls or function applications. And Core Erlang even has let expressions in it. So the semantics itself is defined in a small step style, and that means that we are doing reduction steps on semantic configurations. But that doesn't really mean anything until we define what a semantic configuration is, and it looks something like this. So in this configuration, you can find the frame stack and the regex. And the regex is the expression that we are evaluating, evaluating right now. And the frame stack can be thought of as the continuation for the evaluation. So the regex is just a Core Erlang expression, and the frame stack is a stack of frames. And the frame is basically a Core Erlang expression with a little hole inside it. And the idea here is that when we calculate the value of the regex, it will fit in that hole at the top frame. So the frame at the top of the stack. So this is what the semantic configuration is. And these configurations can be thought of as a snapshot during the evaluation. So this is one of the configurations during the evaluation of this expression: 1 + 2 + 3 + 4. And what is a reduction? So a reduction is basically an evaluation step, and it gets us from one configuration to a new configuration. And to give formal rules, so to give rules to formalize a programming language is basically the act of defining these reduction rules. And if we have these reduction rules defined, then we can evaluate some programs. So here are some reduction rules. So this is how a call expression should be evaluated. So the first step is, if we find call expression on the regex, and you can recall that the regex is the expression that we are evaluating right now, then what we need to do is we need to put it on top of the frame stack and then start evaluating the expression of the module name. And once we've got a value for that module name, the next thing that we need to do is evaluate the expression for the function name. After we get the function name, we proceed to the first parameter of this function call. And the next rule looks a bit scary. It's not actually that scary. So if a parameter of a function was calculated, then we need to put it in and go on to the next parameter. And after we get to the end, what we need to do is call this eval auxiliary function. And what this does is basically so this formalizes the built-in functions in Core Erlang. So, and here is an example evaluation for the ones here who are more visual learners. So we have a Core Erlang expression on the stack. Oh, and I should say that so this is the expression that we need to evaluate, and this is the initial configuration. So the expression is in the redx, and the frame stack is left empty. So we have this expression in the redx, and we just need to follow the rules. So the first rule was, if we have a call expression, we need to put it on top of the frame stack, and then this module expression needs to be evaluated. And luckily, that is pretty easy. The value of this expression Erlang is just Erlang. So we need to then put it in the little hole and go on with the function name. And the function name, similarly, the value of this is just plus. So we put it in the little hole and go on with the parameters. The first parameter is 1. It has a value of 1. So we put it in and move on to the next parameter. And this is a bit more interesting because again we have a function call here. So we need the first rule again, which was to put the call on top of the frame stack and then go along with the module name. And I think that you can guess what happens next. So continuing after a few steps, we get here. So we have 3 on the redx. The value of that is 3, and now we need the rest rule. So we have this eval of this call, and I said that this was just an auxiliary function. So this just needs to be calculated. So this is not even a reduction step. We calculate the function, 2 plus 3 is 5. And then we use the same rule again. And similarly, 1 plus 5 is 6. So yeah, and this is an end configuration because this configuration cannot be reduced any further. So, and another bit of notation, so this arrow with the star on top of it is a multi-step reduction. So in multiple steps, we get from that configuration to this configuration. So and all of this that you've seen here is only this bottom layer of the semantics, the sequential layer, and the upper 2 layers are concerned with formalizing the Erlang actor model. But this paper doesn't talk about them, so I won't go into it here. I will need to go into this in my next talk. But just remember, this is just the bottom layer. So I need to talk about atom exhaustion a bit. So in Erlang systems and in Beam systems in general, atoms are stored in a so-called atom table. So every time we create a new atom, it will go into the atom table. And an important property of this atom table is that it has a fixed size, and it also never gets garbage collected. So after a while, the atom table will get filled up with atoms, And if we want to, my computer is about to die. Sorry. It's plugged in. I don't see all that. Thank you. So yeah. So where was I? So the size of the atom table is limited, and if we fill up this atom table, the default capacity of this atom table is 2 to the 20, so around 1 million atoms. But if we fill it up and we try to create another atom, then there is no more room to it. So what we get is a crash. So the Erlang crashes, and we will need to restart it manually. And the most common way that this problem would occur is during dynamic atom creation. So with functions like list to atom or binary to atom. And this is a function that is vulnerable to atom exhaustion. And in the real world, this is probably not what you would see if we were talking about applications vulnerable to atom exhaustion. But this is just a toy example to show us. So basically, if you input a number to this function, it creates that number of atoms. And as you can see, if the input number is big enough, then we indeed cause atom exhaustion. So how do we formalize? So how do we put in this atom exhaustion to a formalization? Well, the first thing that needs to be done is formalizing side effects. So if you remember this auxiliary function eval, it gives back the result of the built-in functions, but we can also give back a side effect along with these results. And the side effects are things like reading operations or writing operations, or what you care about here really is atom creation. And so every time, and this effect is an option because we might not get a side effect from a single from this evaluation, but we might get it. And so this is an example with list to atom. So previously, evaluating list to atom full would just give us the atom full, but with this new version, along with the atom full, we also get an atom creation side effect. So the next thing that needs to be done is to label our arrows. So if you remember this rule of function calls, we now need to rewrite it like this. And this line means that the thing about it is a precondition. So eval now has two arguments, a result and the potential side effect. And the result goes in the regex as before, but the side effect will be put on the arrow. And we also need to talk about the many-step relation again, which is formally called the reflexive transitive closure. And really, this is just an n-step relation and not a many-step relation. And an n-step relation can be two things. It can either be a zero step or a more than zero step. And if we do zero steps on a configuration, we just get the same configuration. And this is where reflexive comes from. And this is the transitive rule. So basically, if we get from the starting configuration and we do one step to an intermediate configuration, and then if we do n steps to get to this ending configuration, then what that really means is we did n plus 1 steps here. And so these rules need to be modified because what we have done with the single steps is label them with potential side effects. And what we want to do with the multi-step relations is we want to give back the list of side effects that were generated along the way. So here is how the rules need to be rewritten. So if we do 0 steps, then we didn't then we didn't do any side effects along the way. But in the transitive case, so we might have a side effect in the first step, and for the end step on top, this big L means a list of side effects, and on the bottom we will have a big L prime, and to calculate that big L prime is to do this. So basically, if during the first step we didn't have a side effect, then the list of the rest of the side effects will be given back. But if we did, then the side effect will be put into L prime, and also this L label needs to be put for the many-step relation as well. So formalizing atomic exhaustion in this semantics could be done in 2 different ways. The first one is to actually formalize the atom table, and this would be more faithful to the Erlang language. The problem is we wanted to formalize atom exhaustion for the upper 2 layers of the semantics as well, but that would be pretty hard to implement if we did it this way. So this is the other way to do it, and so since we have this reflexive transitive closure with a list of side effects along the way, we can just trace the atom creations during the evaluation. And this 2-atom set helper function just transforms this list of side effects and gives us the set of atoms that was created along the way. And we also need to define 2 more things. One of them is the atom value set, or AVS, which is a set of already created atoms, and the other is the atom limit, or the maximum number of atoms that can be created. And if we have all of these, we can define what it means for a configuration to lead to atom exhaustion. But it means it means that 2 things need to happen. The configuration needs to lead to another configuration while generating this list of side effects L along the way. And the other thing is if you get the atom set, so if you get the set of atoms that was created along the way, and take away all the atoms that were already in the atom value set, so the atoms that were already created, the number of this set needs to be bigger than the atom limit minus the size of the atom value set, and this is notated like this. So, and it can be read as follows. So, given the atom value set AVS and the atom limit, this configuration KR will lead to atom exhaustion. And now we can also define what it means for a program to be vulnerable to atom exhaustion. And if you remember, the program evaluation always started with putting the program in the Redux and having an empty configuration. So in this case, we are starting the program evaluation. So that is why the atom value set, which is a set of already created atoms, is empty. For a program to be vulnerable to atom exhaustion, means that given an empty AVS and an atom limit, this configuration will lead to atom exhaustion. So what if we need to prove that that the program R is vulnerable to atom exhaustion? So we formalize the atom exhaustion. We need to prove this for a given R. But so this is just some notation that can be unfolded into this, and this is also just some notation that could be unfolded into this, which just looks frankly disgusting. However, there are a couple empty sets here, so maybe it would clear up, but not really. So what this bottom expression really means is the following. So there exists a configuration and a list of side effects, so that we get that configuration from R while producing those side effects, and the side effects exhaust the atom limit. And the thing is, this is very hard to prove in ROC, and specifically because of this conjunction. So in ROC, a conjunction needs to be proven one side at a time. But these two sides of this conjunction are very interdependent on each other. So we can either prove the left side first or the right side first. But going either way is not very feasible. So this cannot really be automated. So that is why the Galois calculus was developed. And Galois stands for generates at least n unique atoms. And the idea with this calculus was to not use this two atom set L, and actually to not use the side effects collected along the way in general, but to just prove that at least n atoms get generated when evaluating the program. And this is the notation for Galois, and it can be read as follows. So given AVS, the configuration KNR generates at least n unique atoms. So Galois has three rules to it. The first one states that any configuration will generate at least zero number of atoms. And so that is an axiom, and it's pretty easy to see why. The next rule says so if we get from this configuration, this initial K and R configuration to K prime R prime in just one step, it is enough to prove. So to prove that this initial configuration K and R generates at least n unique atoms, it is enough to prove that this configuration generates at least n unique atoms. So what this rule says is we didn't generate a unique atom at the first step. And the last rule says it looks a bit complicated. It's actually not that complex. What this rule says is if during the first step there was an atom creation side effect, and the created atom AV has not already been generated yet, so it's not in the AVS, then to prove that we generate n+1 atoms during the calculation of this, you only really need to prove this, which is that we generate n atoms while evaluating from this configuration. So there were a lot of theorems proven about this calculus, and the formal proofs were done in ROC, but the paper is a bit less formal about them, and I want to be even less formal. So the two theorems to remember here is soundness and completeness. So it was proven that if with Ganua, we can say that this configuration generates at least this number of atoms, then the configuration will lead to atom exhaustion. And completeness is the opposite. So if this configuration leads to atom exhaustion, then it will generate at least this number of atoms. And this is great for us because I mentioned that this atom exhaustion formalization cannot be proven automatically. However, the rules of Ganua can be proven automatically. And so if we need to prove one of these atom exhaustion properties to a given program, we can just use this completeness theorem to convert this atom exhaustion, this vulnerability to atom exhaustion into Ganua. The Ganua can be solved automatically with just one theorem in rock. So here is a bit of an example evaluation. So this was the toy example of a program that is vulnerable to atom exhaustion. But this is in Erlang, and I said that the formal semantics is in Core Erlang. So in Core Erlang, it would look a bit like this, and this actually has a few meta variables in it, but you can just ignore them for now. And this figure is straight from the paper because I didn't want to recreate it in PowerPoint. So the thing that needs to be proven here is the following. So we know that this program will be vulnerable to atom exhaustion because for any atom limit that could be set for the size of the atom table, we can give a big enough n that we can exhaust the number of atoms. So for this example, the atom limit was set to be 2, and what that means is that if we generate at least 3 atoms, then the program will be vulnerable to atom exhaustion. And so this is a simplified derivation tree of this proof, and there are many notations in here, but the things to keep in mind is this at the bottom. So it says that program will generate at least 3 unique atoms during the evaluation, and for most of these steps we are not generating any atoms. So that non-generating rule needs to be applied. But when we are generating atoms, we always have this P on top of the frame stack, and I didn't put it here, but this P frame contains that leads to atom built-in function that actually does the atom creation side effect. So that is why when a step is done on this configuration, we generate an atom along the way, and we only need to prove that instead of generating just 3 atoms, we only need to prove that we generate 2 more atoms along the way, and then 1, and then we get to 0, and we know that is an axiom because every program generates at least 0 atoms along the way. And here are some final thoughts for this. So this Ganua calculus could be extended to the concurrent layers of the semantics as well. We have some ideas for that. And Galva is actually pretty general. And the ideas developed here could be used in the formalization of other vulnerabilities, and we can reason about them as well. And the final thought here is that formal verification works well alongside static analysis tools. So you might be wondering, so why are we proving that that a program is vulnerable to atomic exhaustion? Shouldn't it be better to prove that the program is not vulnerable to atomic exhaustion? But formal verification and static analysis tools have the same goal in mind, which is to find vulnerabilities in programs. But static analysis tools can give false positives. But by the nature of formal verification, that cannot give back false positives. So these two tools can work very well in tandem together. So if a static analysis tool says that this program might be vulnerable to atomic exhaustion, then we can check using formal verification that it is indeed vulnerable to this program. And before before I forget, I would like to thank Arsenii Fomin for his work on this paper, because this was actually his master's thesis work, and he really should have been the one to give this talk, but unfortunately his travel couldn't be arranged because of visa issues. But I want to thank you all for listening, and I think we might still have a couple of minutes for questions if you have any.
We have time for one question.
Okay.
In your closing thoughts, you mentioned other vulnerabilities. Are these all related to exhaustion, or do you have other vulnerabilities, right?
But it would be great to ask Arsenii about that because he really wanted me to. So he has many other ideas for this, but he was the main contributor on this paper, and I just came in at the last minute to help out. So yeah.
Thanks for the talk. Just one question. So I was wondering, is the Gamma language too incomplete? Because I'm wondering if you can, because basically, if understood, you need to execute the Redux inside the Gamma. So I was wondering about how impressive is the language, and if it will always eventually.
So we'll always eventually terminate. So the semantics itself. So the semantics rules themselves. So basically, there could exist an example where just executing the rules will. So basically, we can get infinite recursion here with these semantic rules, and so that is an interesting question, and I would need to go into a bit of ROC for this. So in the ROC theorem prover, infinite recursion is actually not possible, and that is because I mentioned that ROC uses constructive logic, and if we allowed constructive logic, if we allowed infinite recursion in constructive logic, that could lead to logical inconsistencies. So for the definitional language of ROC, which is called that is called Galina, by the way. You cannot have infinite recursion. However, in the tactic language of Rock, you could have infinite recursion. So if I thought about it, so basically, if we did have an infinitely recursive program, then that Rock tactic shouldn't ever. So we shouldn't ever get to the end of that Rock tactic, basically. Right. Should I move on to the next talk?